Hi, today we're going to talk about valence shell electron pair repulsion, also known as VSEPR for short, and how we use it to determine the geometry of a molecule. So in our last video we talked about why atoms form hybrid orbitals in order to bond. I'm going to link that video below. And I mentioned the whole idea behind valence shell electron pair repulsion is that electron pairs are going to push each other as far away as possible. And again, I'm going to also drop a link to the video I mentioned in that video, the one with the guy with the balloons, that shows how this ends up working out in practice. So basically, here's what happens. When you have two things bonding, then you end up with what we call a linear configuration, where the two things are separated by each other by 180 degrees. If you have three things bonding to a central atom, essentially you have a trigonal planar geometry. So everything is in one plane and they're 120 degrees apart. Once you get more than three things bonding, you're going to end up with a 109.5 degrees angle, which is what we call a tetrahedral geometry. And if you have five things bonding, you get this interesting geometry that we call trigonal bipyramidal, where you get three of the bonded things in a plane 120 degrees apart, and then you have one up and one down at 90 degrees to that plane. And then finally we have octahedral, which despite the prefix octa, this is six things bonding, not eight. If you connect all the corners, you would basically make an eight-sided shape. That's why it's octahedral. Here, all of the atoms are at 90 degrees to each other. So those are the geometries that we're going to be working with. And again, in class, we're going to link these geometries with valence bond theory and hybrid orbitals. So that is a part I'm not putting in the video. So in order to understand what sort of geometry that we have, what we need to do is we need to look at what we call electron domains. And an electron domain is basically an area where electrons gather around the central atom. So we can have two types. We can have a bonding domain. That could be a single bond. It could be a double bond. And importantly, a double bond counts as one single bonding domain. A triple bond also counts as one single electron domain. The other type of electron domain we have is a non-bonding domain. These are unshared electrons. Some people call those lone pairs. I usually stick to non-bonding electrons. But again, those are going to come in pairs. So we're either going to have bonding electrons or non-bonding electrons. We've talked about those as we did Lewis structures. But the important thing to know here is that multiple bonds count as one electron domain because all those electrons are in approximately the same area. So in order to determine the molecular shape, the first thing we're going to do is we're going to draw a Lewis structure. And again, I'll drop links to my Lewis structure videos down below. We're going to locate central atoms. Now, this is important. If you have a small molecule like the ones we're doing on this video, there's only going to be one central atom. But anything that has more than one atom bonded to it is considered a central atom. And you have to find the geometry around each central atom separately. So for each central atom, then, you're going to count how many bonding domains it has and how many non-bonding electron domains it has. You will use the total number of both bonding and non-bonding domains to determine what we call the electron domain geometry, which is how the electrons are arranged. And then we're going to use the number of bonding domains to determine the molecular geometry, which is how the nuclei of the various atoms are arranged. And as we go through and we work examples, you will see the difference between electron domain geometry and molecular geometry. What I'm going to do here is I'm going to show you the difference between electron domains and molecular geometry. So we mentioned that if you have three electron domains, then you have trigonal planar geometry. Basically what we're going to do is we're going to create a family of molecular geometries that are based on this trigonal planar archetype. And what the molecular geometry depends on is how many of those are bonding domains. So if you have three bonding domains, your molecular geometry is also trigonal planar. But if you only have two bonding domains, and then that third electron domain is just a non-bonding pair of electrons, we call that molecular geometry bent. Why is the molecular geometry and the electron domain geometry different? It's because when we look at these molecules using a tool like X-ray diffraction, we cannot see the non-bonding electrons. We can only see the nuclei of the atoms. So this is what we see. We see that central atom that I've marked in red here. We see the two bonded atoms, which I've marked in green, but we don't actually see that pair of electrons that I've put in a dashed line for. They affect the geometry because the non-bonding electrons will repel the bonding electrons, but they're not going to be visible to us. So that's why we differentiate between electron domain geometry and molecular geometry. And the reason I haven't talked about two electron domains is because if you have two electron domains and one of them is a non-bonding pair, you only have one thing actually bonded. It's not really a central atom then, and so we don't determine the geometry for that. So let's go on and look at four electron domains. Again, the base type for this is tetrahedral. Everything that has four electron domains is going to have a tetrahedral electron domain geometry. If all of those four electron domains are bonding domains, then the molecular geometry is also tetrahedral. If we have one non-bonding electron domain and three bonding, then we get this molecular geometry that we call trigonal pyramidal. You could see this is different from what we looked at earlier, where we only had three bonding and no non-bonding domains, because this one is actually not planar. It forms a very flat pyramid. And if you have two non-bonding and two bonding domains, you're going to end up with another bent configuration. The difference between the trigonal planar bent and the tetrahedral bent is that the trigonal planar bent has a 120-degree bond angle roughly, and the tetrahedral bent is going to have something that's more like 109.5. And I say approximately because these things do vary, and we'll talk about that more in class. So now let's move ahead and do 5 electron domains. Remember here, the archetype here is the trigonal bipyramidal, and if all 5 of those are bonding domains, then the molecular geometry is also trigonal bipyramidal. If we have to remove one of these bonds to make it a non-bonding electron, we have a choice. We could take away one of these atoms here in the plane of 3, and we call those the equatorial ones, or we can take one of these that go up and down from that plane, what we call the axial atoms. As it turns out, the way to get rid of the most electron repulsion is to take away one of these equatorial electrons like this, and it makes what we call a sawhorse molecular geometry. And it doesn't look like a sawhorse right now, but it turns out if you rotate it 90 degrees, it does kind of look like a sawhorse. Then if we have 2 non-bonding domains, we end up with what we call a T-shaped geometry. And then if you have 3 non-bonding domains, you end up with a linear configuration. And finally, let's do 6 electron domains. Here we have the octahedral geometry as our archetype. That's both for the electron domains as well as the molecular geometry of anything with 6 bonding domains. If you take away 1, you end up with this square pyramidal where 4 of the bonded atoms are in a plane, and then the 5th goes upwards at 90 degrees. If we have 2, we end up with what we call square planar. If we have 3, we end up with another T-shaped thing. And then if we have 4, we end up with a linear configuration again. Okay, so what we're going to do is we're going to go ahead and we're going to find the geometry of a molecule we've talked about in regards to bonding, and that is methane, CH4. So our first step is to draw the Lewis structure. And I'm just going to go ahead and draw the Lewis structures for you in this video. If you want, you can take the time to pause the video and do those Lewis structures yourself, just to double check my work. Next, we find the central atom. There is only one here, and that is carbon. And around carbon, we're going to count the bonding and the non-bonding electron domains. Well, you can see that we have 4 bonds that have formed here. We have no non-bonding domains because there are no unshared electrons. And so we have a total of 4 electron domains. That means our electron domain geometry is going to be tetrahedral. How about our molecular geometry? Here again, we have to look to see how many non-bonding domains we have. We have 0. So our molecular geometry is going to be the same as our electron domain geometry. Now we're going to find the geometry of arsenic trihydride. And I'm just going to draw the Lewis structure here. It's going to look like this. And our central atom here is going to be the arsenic. It's never going to be hydrogen. So let's count our bonding and our non-bonding electron domains. You can see we have 3 bonded atoms, so that's 3 bonding domains. We have 1 pair of non-bonding electrons, so that's 1 of those. Again, we have a total of 4, which tells us that our electron domain geometry is going to be tetrahedral again. But remember that we now have 1 non-bonding pair, so our molecular geometry is going to be trigonal pyramidal. Finally, let's do xenon tetrafluoride. We'll start out with a Lewis structure. And again, I highly encourage you to go through and double check my Lewis structure because this is kind of a fun one to do. So here's the Lewis structure. The central atom is going to be xenon. That's pretty obvious. And then we're going to count the bonding and the non-bonding electron domains. So we have 4 atoms bonded, so that's 4 bonding domains. We have 2 non-bonding domains. That gives us a total of 6 electron domains for this molecule. So now our electron domain geometry, because it has 6 electron domains, this is going to be octahedral. And our molecular geometry, because we have 2 non-bonding domains, is going to give us square planar geometry. VSEPR basically helps us determine what molecules look like in 3 dimensions, and that's really important because the 3-dimensional structure of a molecule helps us understand how they react with each other. This is something that requires a lot of practice to get good at, and so we're going to work on this a lot in class. I hope this was helpful, and I look forward to seeing you again soon.